You know, color mixing can be a real chore, but it's actually not that hard to understand. The caveat, though, is that it really helps to understand light reflectance and color vision in order to get it. If you've ever been in a science class, you've seen a chart of the electromagnetic spectrum, BFD, right? But look at the frequency around 10 to the 14th power. That's our spectrum of visible light. A lot of the red and violet at both ends gets cut off because the red and violet beyond a very specific range of frequencies and wavelengths extends into the infrared or ultraviolet range. The colors across the visible spectrum are pure, so imagine the bright colors you have unmixed and you get the idea. A little like a kid's watercolor set, isn't it?
But I'm an adult now!
Only legally.
Oh.
Everything we see reflects or emits wavelengths. In the stovetop's case, it's emitting wavelengths in the ballpark of 1000 Kelvin, while my daylight bulb emits wavelengths around 5000 Kelvin. Notice that at higher temperatures, the wavelengths become blue.
Yeah, according to the law of physics, blue is literally hotter than red. Science laughs in the face of our art jargon.
I guess John Ruskin was right on the money with this one. Woo! When you see color, light hits the rods and cones in your retina. That signal travels along your optic nerve to the occipital lobe in the back of your brain. Rods don't play much of a role in color vision. They're mostly about night vision, though. So if you wander around in the middle of the night and bang your shin on your easel, they're the ones you have to thank. Cones are responsible for color vision, and there's three types. S cones, which are most sensitive to blue-violet wavelengths, M cones, which are most sensitive to green wavelengths, and L cones, which are most sensitive to greenish-yellow wavelengths.
What relevance does any of this have to color mixing?
Funny you should ask. Color mixtures are informed by the light your paints reflect, and reflected light stimulates our eye to varying degrees. Nicolazzo yellow is an orange-yellow, but it's still yellow, so it reflects red, orange, yellow, and green light. Phthalo green yellow shade reflects green, but also blue, cyan, and yellow. When combined, the red and orange light reflectance is reduced, while the green reflectance is bolstered and the yellow reflectance remains strong. Your eye interprets this as an increase in M-cone stimulation. The only reason this green isn't brighter is because Nicolazzo yellow reflects less light than a traditional primary yellow paint.
You can tell what color a light reflects with a spectrometer, but those are $2,000! That's next year's healthcare premium. Good thing we're artists, not scientists. So, we can make an educated guess based on the color's appearance.
Phthalo blue-green shade is a greenish-blue or cyan color, so it's going to mix violets and greens with about equal saturation. Quinacridone magenta is a violet-red or magenta color, so it's going to mix oranges and violets with about equal saturation. And Nicolazzo yellow? Well, I'm not doing that one again. Try to keep up. When we think about material colors in relation to visible light, it helps to take the spectrum and turn it into a circle called a color wheel, because of the circular way colors mix. Yellow and magenta make orange, cyan and magenta make violet, and cyan and yellow make green, and repeat into infinity.
There's 5 simple rules for mixing color. Number 1, if you want bright mixtures, you gotta use bright colors. It's really obvious, but if you want bright purple, you probably shouldn't use Perylene Maroon and Indanthrone Blue. Unless you just want dull purple. But I wanted Joker purple. Number 2, the brightest mix will always come from 2 colors closest to each other on the color wheel.
Pop quiz time. If you have a bright magenta, a bright orange, and a bright yellow, which 2 are going to mix a brighter red?
The magenta and orange! I just blew your f***ing mind, didn't I? Number 3, to neutralize a color, always use its complement.
Most colors have a mixing complement. Keyword, most. I'm looking at you, yellow. Middle yellow's a real ball breaker of a color. You gotta mix it with 3 colors every time you want to neutralize it.
WTF, man? It's because yellow's unusually good at reflecting red and green light.
And besides that, we don't have any violets that can totally cancel out the red and green light. My sentiments exactly.
Number 4! If your mix contains more than 3 colors, you're doing it wrong.
No.
Number 5! The harder it feels, the fewer colors you need.
Seriously, at the point you can't tell the difference between phthalo green blue shade and yellow shade, it's time to downsize. There's a reason I use cobalt green and sap green now. It's because I can pick them out of a lineup.
But wait! You forgot the sixth one! Although color appearance and light reflectance are good ways to predict a color mixture, paints are weird sometimes and they don't do what you think they should.
Don't judge me. Don't even look at me.
For instance, nickel azure yellow shifts toward middle yellow intense and pyro orange mixes brighter violets than you think it would. So the best way to get better at color mixing is to mix your paints frequently. Reality is a harsh mistress. Would you like to play a game? Woo! It's time for Anal Squares! Woo? It's pronounced analogous, butthead!
What I'm doing here is painting strips that go up and down or straight across, and I'm building a staircase with them. And I'm doing that with 3 colors at a time, hence the term analogous. And when I do that, I get 3 different color mixes out of it. Here I got my yellow orange, my deep red, and my bright red. Now I'm going to do it with violet, blue, magenta, and orange red. I'm going to get 3 different mixes, because they're a different set of colors. I'm going to get my bright red still, but I'm also going to get a very dull purple, and I'm going to get a very bright purple. Moving on! Here we got green, cyan, and violet blue, and now we're getting really into the cool side of things, aren't we? That's right, man. That's right. I got my middle blue, I got my turquoises, deep turquoise and bright turquoise, and now I'm gonna dance. Sometimes you gotta take a break, feel the groove. Alright, back! And we're back with magenta and violet blue and cyan. Because guess what's gonna happen now? I'm gonna get that bright purple again. I'm gonna get deep purple. And I'm gonna get another middle blue out of it. Ooh, the power predictions are incredible, aren't they? Yeah, that's right. I'm a color psychic. Oh. Next up on deck, we got cyan green and yellow green. And guess what's gonna, well, not yellow, but we do have yellow green. Look at this. This exercise is so much fun. I love my squares, my analogous squares, or my analogous squares. Last of the bunch, and the last interesting color mix you can see there is that dull green. Try it out, man.
Well, that covers all of them except for the compliments.
Ugh, you're right. Fine, here they are.
I thought you said they were compliments.
They're close enough.
One of them's green.
Didn't you listen to anything I said about yellow?
Honestly, I zoned out as soon as you said color.
And with that... Remember that the best colors to learn with are nickel azo yellow, pyro orange, quinacridone magenta, ultramarine blue, phthalo blue green shade, and phthalo green yellow shade. It's best to use a model based on cyan, magenta, and yellow because cyan reflects blue and green light about evenly, magenta reflects blue and red light about evenly, and yellow reflects green and red light about evenly. With those 3, there's an even distribution across our color perception. One of the most popular alternatives to the secondary setup is the split primary system. The reason split primary color theory fails is because it relies on a traditional red, yellow, and blue color model supported by the rationale that primaries are tainted. Therefore, we need 2 versions of every primary to make up the difference. But the problem isn't that primary colors are tainted, the problem is that red and blue aren't primary colors. And this is demonstrably true, because if they were primary colors, these secondary mixes would be equal in saturation, but they aren't, and instead cyan, magenta, and yellow produce equilibrium. The reason for this is that blue reflects more violet than green, and red reflects more orange than violet. Or in other words, red stimulates L cones very strongly, and blue stimulates S cones very strongly. The split primary system works better in practice than theory because it's effectively a secondary palette with a second yellow instead of green. The problem with this is that yellows aren't so different. That's why a lot of split primary users literally select orange and call it a warm yellow. I know, right? But if you linger around lemon and primary yellow like the theory dictates, you'll notice that the oranges and greens are woefully similar, because there isn't enough red and green reflectance one way or the other to make a difference. Ditch the lemon yellow for phthalo green yellow shade, and equilibrium is restored. All is right with the world. Sorry, lemon yellow, you lose. The end. Soulkeeper out. Now, if you excuse me, I've got some elbows to drop on split primary color theory. What do you think of that?
Woo! That's right.